In this session, let us have a discussion on torsional vibration. Consider a system of a shaft of one of which end is fixed and other end carries a circular disc. So whenever the shaft is made to twist, the particle in the shaft or the disc may have a rotation on the circular fashion around the axis of the shaft. Here, the particle and the shaft is said to be under torsional vibratory motion. So, whenever the particles of a shaft or disc moves in a circle about the axis of the shaft, the vibrating motion is called torsional vibration. So here the shaft is twisted and untwisted alternatively, then so that the shaft is induced with the torsional shear stress. Let us have here the formula for the natural frequency of the free torsional vibration. So here the shaft is of negligible mass as shown in the system, carries a disc on one of its ends. Here, the after the time t, the disk is twisted through the angle theta. So here, the restoring force Q into theta. Here, the Q equal to the torsional stiffness. Torsional stiffness. So restoring force is Q into theta. Then the accelerating force I into d squared theta by dt squared. So the both are equated for the equilibrium condition. So one is put the minus n as the opposite motion. So we have the equation. Here the equation resembles the equation of the simple harmonic motion. So the Q, the omega can be replaced by square root of Q by I. Comparing the simple harmonic motion and our equation, in the space of omega squared, Q by I and omega equal to square root of Q by IL, Q by I. So it is a angular speed. Then time period Tp equal to, as we know, 2 by omega. Again, natural frequency is inverse of the time period, that is 1 by Tp. So 1 by 2.5 into square root of Q by I. So it is a formula for the natural frequency of the free torsional vibration. Here, already we have discussed the torsional stiffness. So we have the torsion equation as we know that T by J equal to C theta by L. So J is the polar moment of inertia of the material of the shaft. C is the modulus of rigidity of the material of the shaft. So T by theta equal to Cj divided by L. So the T by theta is called torsional stiffness Q. This Q equal to Cj by L. So let us have a simple problem. A flywheel is mounted on a vertical shaft. Vertical shaft as shown in diagram. So the ends of the shafts are fixed and its diameter is the 50 mm. The flywheel has a mass of 500 kg and its radius of gyration is 0.5 meter. Find the natural frequency of the torsional vibration if the modulus of the rigidity of the shaft material is 80 gigameter per meter square. So the diameter of the shaft is 50 mm. Then the mass of the flywheel is 500 kg. Its radius of gyration 0.5 meter and the G is 80 giganewton per meter square. That is the system. You have to find natural frequency. So directly substituting the values of the components in the formula. So now in the formula we have the J. So polar moment of inertia of the material shaft of the shaft J way by 32 into d power 4. And torsional stiffness equal to, first we can have the two portions. So the above the flywheel and below the flywheel. So the upper portion of length L1 and the bottom portion is of length L2. So for the portion L1, Q equal to Cj L1. Simply substituting, we have Q1 equal to here. Then considering the bottom length L2, again Qt equal to Cj by L2, 84 into 10 power 3 Newton meter. So total stiffness Q equal to Q1 plus Q2. So mass moment of inertia equal to mk square. So simply substituting the Qi at the J, we can have the find out the natural frequency 1 by 2 by into square root of Qi. All we have. So Fn equal to 5.32 Hz. Now, next case is the again the same frequency of the free torsional vibration of a single rotor system. So in our engineering application, the shaft may be applied or assembled with many rotating elements like pulley, sprocket, gears, etc. So it can be generally termed under the name rotor. So a shaft is applied with a single rotor at its end, and one end is fixed. Here, the one end of the shaft is fixed and another is fitted with one rotor. So we have the frequency formula 1 by 2 into square root of Q by I. Again, substituting the value of Q Cj by L. Now the maximum amplitude of vibration at the free end, as we know, with the value of with the amount A, and on the fixed end, the vibration is 0. Here we have the point called node. Here the amplitude of torsional vibration is 0 at the fixed end. The point is called node. Here the shaft remains unaffected or no movement on due to the vibration. Here the point is called node or nodal point. Again, the same shaft can be also applied for the two rotor at each at one end. So for the shaft to be twisted, so the two rotors must rotate in the opposite direction to each other. If rotor A rotates in the clockwise direction, the rotor B should rotate in the anti-clockwise direction so that the shaft can be twisted. Here, the maximum amplitude of vibration at both ends A and B of amplitude A1 and A2. So here at the middle of the shaft, there is no vibration. That is, we have the node point. So the portion can be considered as a two portion LA and LB. Here L is the fixed point, and the shaft can be termed as separated as two separate shaft of length LA and LB. That is PN and NQ. So considering the portion LA, here in the LA is the distance of node point from the end A, and LB is the distance of node from the end B. So considering the portion for the rotor A, Fn A equal to 1 by 2 into Cj divided by LA into Ia. For the portion for the rotor B, Fn B equal to 1 by 2 into square root of Cj by LB into Ib. Again, let us have a point have the two rotor must have the same frequency. So equating the fourth frequency of the rotors A and B, Fn A equal to Fn B. So the neglecting the common terms is C and J, we have the equation LA into Ia equal to LB into Ib. From that equation, the nodal distance can be found, and also the length of the nodal distance can be also came to be known. So this is the single rotor system and the two rotor system. In the next class, we can have the discussion on the three rotor system. Thank you for listening.